see a robot fail at a really simple task, like smashing a coffee cup right through a table instead of setting it down gently? That happens because motors and actuators on their own are essentially dumb muscle. If you give them electricity, they just spin. They have no idea when to stop. To get that muscle to do something useful, it needs a brain. In electronics, we call this the controller. It's the piece of the system that dictates exactly how fast the motor should go, which direction it should turn, and the exact moment it needs to hit the brakes. Raw mechanical power requires digital intelligence to turn chaotic force into precise, deliberate motion. Imagine trying to walk perfectly straight to a target across the room, but you're wearing a blindfold. You take 10 steps and just hope you've arrived, but you could be completely off course. We call this an open-loop system. On the left side of this diagram, you see an open-loop system. The controller sends a command down to the motor, and the interaction ends. It never checks the output to see if the motor did what it was told. Now, imagine taking off the blindfold. You take a step, you see where you are, and you adjust your next step based on what you see. That continuous checking is called a closed-loop system. On the right side of the diagram, notice the addition of a sensor, like this encoder attached to the motor. It measures the physical motion and sends that data right back up to the controller. The brain is constantly comparing what the motor is actually doing to what it is supposed to be doing. That continuous loop of checking and adjusting is the dividing line between a machine that simply guesses and one that actually knows its position. So if a digital brain only speaks in ones and zeros, meaning a signal is either completely on or completely off, how does it tell a physical motor to run at exactly half speed? You might think you could just feed the motor half the voltage, but doing that physically restricts the electricity, causing the components to burn off all that unused voltage as heat. It wastes a massive amount of energy. Instead, engineers use a clever trick called pulse width modulation, or PWM. Think of it like driving a car on the highway. Instead of holding the gas pedal down halfway, imagine rapidly tapping the pedal to the floor over and over to maintain your speed. This chart shows how electrical tapping looks in practice. We call this the duty cycle. If you keep the pedal down longer during each tap, like the 75% wave, the motor receives more power. If you shorten the tap, it slows down. This tapping doesn't happen just once a second. The digital controller pulses that power thousands of times every single second. To the heavy motor, it doesn't feel like a stutter. It feels like a perfectly smooth rotation. By rapidly flipping between fully on and fully off, the system avoids burning off excess heat. PWM allows for incredibly precise speed control with almost zero wasted energy. There is a practical problem here, though. The tiny microchip that does all this thinking operates on a fraction of a volt. If you tried to hook it directly to a high-power motor, the chip would instantly melt. To bridge the gap, the system relies on heavy-duty electronic switches called MOSFETs. You can think of them as the muscle-bound translators of the circuit. The weak brain taps out its tiny PWM signals, and the MOSFETs safely flip the high-power electricity on and off to match. This arrangement, an H-bridge, gives total command over electricity flow using 4 switches, Q1 through Q4. Turn on the top left and bottom right switches, and electricity flows forward across the motor. Flip the opposite pair, and current pulls the motor into reverse. The H-bridge serves as the machine's forward and reverse gears, safely turning delicate logic into physical force. Getting a motor up to speed is relatively easy. Making it stop perfectly on a precise target line without jerking back and forth is the hardest part of motion control. This graph shows a system targeting the dotted line. The steep climb is the rise time. Momentum causes it to blow past, the percent overshoot. It overcorrects, and that wavy line shows it oscillating until resting on target. That delay is the settling time. To fix this bumpy ride, engineers use a tool called a PID controller. Think of it as an expert chauffeur that combines 3 distinct math tricks to ensure a perfectly smooth stop. The P stands for proportional. It acts like the gas pedal. If the target line is really far away, P pushes the motor hard. As the motor gets closer, P naturally eases up on the power. The I stands for integral. Think of this as the nudger. If friction causes the machine to stop just a tiny bit short of the finish line, the I calculation builds up a little extra power over time to push the motor right onto the mark. Finally, the D stands for derivative. This acts as the brakes. It looks ahead at how fast the target line is approaching and applies just enough resistance to kill the momentum before it blows past the stop. By balancing the push, the nudge, and the brakes, the PID controller transforms a vibrating machine into a smooth, decisive tool. When you combine the heavy-duty muscle of MOSFETs, the extreme energy efficiency of PWM, and the balancing act of a PID controller, machines are able to perform incredibly complex physical feats. Take a drone hovering in the sky. When a sudden gust of wind knocks off balance, the sensors detect the exact movement, the PID brain calculates the required counterforce, and the PWM throttles the motors, all in a fraction of a second, locking the drone in midair. These calculations manage massive conveyor belts in factories and roll automated blinds to a precise millimeter in modern homes. When a motor is paired with a smart control system, it functions as a reliable, high-precision tool.
It's kind of crazy, but the average home actually contains over 40 electric motors. They're literally everywhere. Today, we're diving into a really fascinating engineering journey. We're going to look at how you take a raw, dumb, spinning shaft and transform it into a highly precise, intelligent actuator. Because, let's face it, without a solid control system, a motor just spins aimlessly. But get the setup right, boom, it becomes the absolute foundation of modern robotics and automation. So, this brings up a huge engineering challenge. How exactly do we make these dumb motors smart? I mean, a raw motor has zero awareness, right? It just spins based on whatever juice you feed it. So how on earth do we give it the pinpoint precision and rock-solid stability you need for, say, complex tasks like positioning a robotic arm or keeping a drone perfectly stabilized in midair? Well, here's our roadmap for comparing this step by step. We'll quickly cover the basics of motor control, then compare open versus closed loops, figure out how to control speed with PWM, steer direction using H-bridges, and finally, we'll perfect all that motion using PID control. It's going to be a fun ride from basic loops to flawless movement, and don't worry, we're leaving the intimidating jargon behind. All right, part 1, the basics. To ground these abstract ideas, let's just use a super simple anatomy analogy. Think of a control system exactly like the human body. The controller, that's your decision-making brain, processing signals and figuring out what needs to happen. The actuator, or the motor, is the muscle that actually does the heavy lifting and creates physical movement. And then you have the sensors, acting as the eyes and nervous system, constantly checking the work and giving feedback. You really need all three working in harmony, otherwise you just can't build a modern, intelligent system that adapts on the fly. Moving on to section 2, open versus closed loops. This is actually the first major upgrade for our system, giving that muscle some much-needed awareness. Check out this comparison. On one side, we've got the open loop system. It blindly follows input commands without ever bothering to check the results. Think of your standard stepper motor. It moves a set number of steps, sure, but if something jams it up, the system is completely clueless. It just happily keeps trying to push. Now, on the flip side, we have the closed-loop system. This is way smarter. It uses sensors to give constant feedback, which lets it automatically correct any errors. A servo motor is basically the textbook example of this in action.
You can really see the difference here. Notice how the open-loop setup is just a straight, one-way street from the controller straight to the output. Nothing comes back. But look at the closed-loop system over there on the right. It relies on an encoder attached right to the back of the motor. That encoder is incredibly important because it routes motion data right back to the controller, literally closing the loop. It constantly checks the actual output against what we want it to do so we can fix mistakes in real time.
Okay, so now our motor has some awareness. Let's hit section 3, controlling speed with PWM. How do we actually tell this smart motor how fast it needs to spin? We pull this off using a really efficient trick called pulse width modulation, or PWM. And the magic of PWM is all about the duty cycle. The duty cycle is just the percentage of time a digital signal is active or on during a single period. It's kind of like pedaling a bike. You don't push down constantly, right? You push in pulses, and how long you push dictates your speed. By tweaking this percentage, we control the average power delivered to the motor. It's a game changer because we can manage speed perfectly without losing efficiency or creating a ton of unwanted heat.
See these graphs going from 0% all the way up to 100%? Notice that we are not changing the maximum voltage amplitude at all. It stays totally locked at 5 volts across the board. Instead, by simply stretching out that digital pulse, increasing the on time, we push up the average output voltage, which you can see as that middle line. A 25% duty cycle means a low average voltage and a slow spin, but bump that up to 75% and boom, you get a much higher average voltage, and the motor speeds up incredibly smoothly.
Awesome. Speed is sorted. Let's jump into section 4, direction and H bridges. Because, well, how do we get the motor to actually throw it in reverse? Enter the H bridge. It's a super clever electronic circuit. And yeah, it gets its name because it literally looks like a giant capital H. It uses 4 transistors or MOSFETs, labeled Q1 through Q4 here. Now, these aren't big, clunky physical relays. They act as lightning-fast electronic switches built right around our central motor, which is that M right in the middle. The secret sauce of this circuit is almost beautifully simple. First step, you activate one diagonal pair of transistors, let's say top left and bottom right. That creates a path for the current to flow through the motor in one direction, spinning it forward. To reverse, you just turn those off and flip on the opposite diagonal pair, top right and bottom left. The current literally reverses its path through the motor. And just like that, it spins backward. It gives us total instantaneous directional control.
All right, so we've got speed and we've got direction. On to our final section, perfecting motion with PID. Because we still need to figure out how to make the motor stop exactly where we want without it violently shaking or totally overshooting the target. To fix all that sloppy movement, we balance 3 specific mathematical terms in what's called a PID controller. P stands for proportional. Think of this like pressing the gas pedal so you can reach your target quickly. But obviously, just mashing the gas isn't a great strategy, so we add I for integral. This slowly nudges us right up to the exact speed limit to wipe out any lingering steady-state errors. Pinpoint accuracy. Finally, D is for derivative. This acts like a shock absorber, predicting the road ahead to dampen oscillation and keep us from wobbling out of control. It's just like the source material points out. PID control reduces error, speeds up response, and increases system stability. By using this 3-part approach as our ultimate mathematical brain, we drastically cut down on unwanted mechanical vibrations. It ensures the actuator performs flawlessly, even when external disturbances or shifting loads try to knock it off course. Honestly, this is the exact same math that keeps a camera drone perfectly stable in heavy winds. When engineers look at a successful control system, they're analyzing its dynamic response. And we're really looking for 3 specific things here. First, a fast rise time, meaning the motor hits the target speed or position really quickly. Second, a low overshoot. We absolutely don't want the system blasting past the target like a car blowing through a stop sign. And third, a stable settling time. We want it locking perfectly into that final position without any lingering wobbles or those annoying jerky little corrections. Take a look at this system response curve. A properly tuned PID loop creates such a beautiful trajectory. You can clearly see that fast rise time right at the beginning. Sure, there's a tiny bit of percent overshoot, which is totally normal for a fast system, but then just look at the settling time. The motor glides gracefully to its set point and just stays there, locked right onto that dashed steady state line. It's absolute proof of the real-world results you get when you combine solid control theory with your sensors and actuators. Wow, okay, we have covered a ton of ground today. Now that you understand how feedback loops give a system awareness, how PWM handles speed so efficiently, how H-bridges steer direction, and how PID math basically transforms a shaky, dumb motor into a razor-sharp precision instrument, well, the possibilities are entirely in your hands. Whether you're building a smart home gadget, a delivery drone, or even a factory conveyor belt, you've got the foundational concepts down. So the only question left is, what intelligent movements are you going to design next? Keep exploring, and hey, thanks for joining me on this explainer.